Newton developed the concept of momentum, or quantity of motion, of an object. He defined the linear momentum of an object, p, as the product of an object's mass, m, and its velocity, v. Note that in this section, we use the term momentum to refer to linear momentum. Later on, when we study rotational motion, we will define another sort of momentum, angular momentum. The SI units for momentum are kilogram meters per second. Since momentum is the product of the mass of an object, which is a scalar quantity, and its velocity, which is a vector, momentum is also a vector. The direction of the momentum vector is the same as the direction of the velocity. So what is the physical meaning of momentum? Let's consider a car and a truck moving at the same speed. Since the truck is heavier than the car has greater momentum than the car. Thus, it takes the truck longer than the car to stop. Similarly, if two identical cars move at different speeds, it will take longer for the faster car to stop. Again, this is because the faster car has greater momentum. Obviously, a speeding truck is more difficult to stop than a lighter, slower moving car. Let's now calculate the momentum of some objects. The momentum of a 2-kilogram ball moving at a constant velocity of 2 meters per second is 4 kilogram meters per second. What is the momentum of a 1.5 kilogram ball going in the opposite direction at a constant speed of 3 meters per second?
Correct.
You probably recall Newton's second law of motion. Did you know that Newton actually wrote this second law in terms of momentum? In modern words, his law would read, the rate of change of the momentum of a body is proportional to the resultant force acting on the body and is in the direction of that force. Let's see how we can derive this equation from the familiar form of Newton's second law. Force equals mass times acceleration. Recall that acceleration is the rate of change of velocity in time, or delta v over delta t. So the force, F, is equal to mass times the rate of change of velocity divided by elapsed time. Delta v is the change in velocity, which is equivalent to the difference between the final and initial velocities. Thus, our equation becomes force equals mass times the difference between the final velocity, v2, and the initial velocity, v1, divided by the elapsed time, delta t. Expanding the equation gives us F equals m times v2 minus m times v1 divided by delta t. But we know that mass times initial velocity v1 is the object's initial momentum, and mass times final velocity v2 is the final momentum. By rewriting the force equation in terms of the rate of change of momentum, we obtain Newton's original definition. From this equation, let's now define an important quantity, the impulse of a force. Multiplying both sides of the equation by delta t gives us force times delta t equals the change in momentum. The impulse of the force is defined as the force multiplied by the time elapsed during the impact of the force. Thus, the impulse is just the change in momentum. We all know why people wear protective helmets and pads, but why do these simple devices work so well at preventing injuries? Let's take a look at the concepts of momentum and impulse and see if we can determine the answer. We can graphically represent the impulse or change in momentum by a rectangle of sides f and delta t. The area of the rectangle is a measure of the change in momentum. This representation illustrates the fact that for a given change in momentum, the force of impact can be very large when the time of impact is very small. On the other hand, if the time of impact is increased for a given change in momentum, the force of impact decreases to keep the product F delta t constant. Cushions, bumpers, and pads used in everyday life use this principle to protect against shocks by increasing the duration of impacts. Let's work through an example. A 1 metric ton car traveling at 72 kilometers per hour. strikes a concrete wall and comes to a full stop in 0.1 seconds. What is the average force of impact exerted on the car? First, let's calculate the change in the car's momentum to determine the impulse due to the collision. Subtract the initial momentum from the final momentum. Since the final velocity of the car is 0, the change in momentum is given by the mass of the car in kilograms multiplied by its initial velocity in meters per second. Notice that the velocity has a minus sign because it is directed in the negative direction in our system of coordinates. The average force exerted on the automobile is given by the change in momentum divided by the duration of the impact. Let's see what happens when we increase the time of impact by placing large foam pads in front of the wall. This time, the duration of impact is 2 seconds. What is the magnitude of the average force of impact now? Correct. Since the impact lasts 20 times longer than the initial impact, while the change in momentum remains the same, the resulting force is 20 times weaker. Now we know the answer to our original question. Protective pads act to increase the time of impact, thereby decreasing the force of impact. With a smaller force of impact, the chance of injury is reduced.